Hello everyone, I'm Yuri Fan from Zhejiang University. Here I present our TSE paper published last year, The Impact of Mislabeled Changes by SZZ on Just-in-Time Defect Prediction. First, I presented the background concepts for understanding our paper. Our work analyzes just-in-time defect prediction, that is, the defect prediction technique that works on changes. The general framework of just-in-time defect prediction is as follows. First, JiT defect prediction uses the SZZ algorithm to label changes from version control systems as buggy or clean. Next, using labeled changes, JiT defect prediction extracts metrics to characterize changes. Based on the labels and metrics of changes, JiT defect prediction learns a prediction model. Finally, for newly submitted changes, JiT defect prediction leverages the model to predict whether the changes are bug introducing or not. In comparison to traditional defect prediction techniques that work with files or packages, JiT defect prediction can help developers inspect and materialize potential risky lines when the modification context is still in developer's mind. The SZZ algorithm generates labeled data for JiT defect prediction, and it is the advent of SZZ that enables such a line of work. The original and basic SZZ algorithm was proposed by Sliversky et al. We refer to this SZZ algorithm as BSZ. After BSZ, researchers proposed several SZZ variants to improve quality of generated data by SZZ. AGSZ was proposed by Kim et al., which deals with changes to comments, blank lines, and formats. Then MASZ was proposed by Dakosa et al., which deals with branch and merge changes. Recently, Nito et al. Proposed RASZ. They further dealt with refactorings based on MASZ. Our paper analyzes these four SZZ variants, and in our paper, we consider that RASZ is less likely to generate mislabeled changes as compared to other SZZ variants. Then we present a motivation or paper. We notice that there are a considerable number of existing studies using BSZ to label changes. BSZ is impacted by large amount of noise. In addition, researchers have raised the concerns for the quality of data used by defect prediction models. For example, whether a bug report reports a real bug, whether the bug and fixing changes are linked, and tangled changes, that is, changes that not only fixing bugs but also do other things. Thus, it is necessary to analyze the impact of mislabeled changes by SZZ on JiT defect prediction models. In this study, we perform an empirical analysis using 10 projects containing over 120,000 of changes. We use a model built using the labeled changes by RASZ as a baseline model. And we compare the models built using BSZ, AGSZ, and MASZ with the baseline model. The study framework is presented as follows. For each studied project, we use auto-sample bootstrap to generate a training set and a testing set. For the training set, we use the four SZZ variants to label the changes. Next, we built four prediction models based on the changes labeled by the four SZZ variants. Then we apply the four models on the testing set. After that, we use SZZ to label the testing set. Finally, we calculate and compare model performance and metric importance for the four models. We iterate this bootstrapped process for 1,000 times. As a result, we found that the mislabeled changes by BSZ and MASZ do not impact the performance of JiT defect prediction models, while mislabeled changes by AGSZ lead to significant performance reduction with an average difference of 1% to 5%. Furthermore, we found that mislabeled changes by BSZ lead to significantly more wasted effort with an average difference of 9% to 10%, and the mislabeled changes by AGSZ lead to 1% to 50% more wasted effort. As for the metric importance of JiT models, we found that most important metric is not impacted by the mislabeling noise, which is the number of modified files in your change. When using naive Bayes and logistic regression as underlying classifier, the top 2 and the top 3 important metrics are impacted by the mislabeling noise. But when using random forest as the underlying classifier, the top 2 and the top 3 metrics are also robust. In summary, in our study, we analyzed the four SZZ variants: BSZ, IGSZ, MASZ, and RASZ. Since the existing studies have used the original SZZ variant, we investigate whether the mislabeled changes by SZZ impact JiT models. We found that mislabeled changes by BSZ and MASZ do not lead to significant performance reduction, while mislabeled changes by AGSZ lead to significant performance reduction. Moreover, we found that mislabeled changes by BSZ lead to significantly more wasted inspection effort. Our experimental results indicate that future studies should use most state-of-the-art SZZ variant, that is RASZ.